Hello, everyone. Let me briefly mention topics covered so far since we finished some significant number of classes in this Bayesian classification. We started first with Bayes decision theory, and from there we proceeded further. So first we have looked into Bayes decision theory. Of course, we discussed on what would be the place of this whole Bayesian classification in terms of our whole course content, machine learning for image processing. Then we had a brief overview of the whole bird's eye view of the whole things. Then we discussed about Bayes decision theory, and then we have discussed about minimizing the error probabilities, total error probability, we were calling it. Minimizing the error probability is what we discussed. After that, another minimization we have talked about. What is that? Minimizing average risk. That's something else we discussed. And of course, in your midterm, you had question on minimizing error probability as well as minimizing average risk. Then we discussed briefly at that time about discriminant functions and decision surfaces. Discriminant functions and decision surfaces. Again, you had one more question coming from here where you had to find out a decision points in case of one-dimensional normal distribution. So in fact, what we did is we have moved there to normal distribution then, and we have spent quite some time because that's the most commonly occurring distribution. So we in fact moved to the Bayesian classification for normal distribution. Right. And in that, what we in fact did was we started with one-dimensional Gaussian distribution to first, right? One-dimensional Gaussian, let me take it, probability density function, let me write it that way. Then, of course, we have discussed about 2D Gaussian PDF. So it is here we have discussed about shape of the ISO curves, etc. We have discussed here. What were the shapes of ISO curves there? By any chance, do you remember? For a 2D Gaussian PDF?
So circle, ellipse.
Right, circles, ellipse, any other possible shape? Rotated ellipses also, right? When you have the covariance matrix, non-diagonal elements also being present, those were the things that we discussed there. And of course, then we had moved to n-dimensional Gaussian PDF, also the expressions for it and all, we have seen it. And then we again did Bayesian classification for 2D Gaussians. In particular, we have taken, so this Bayesian classification for two-dimensional normal distribution or Gaussian, you could call any of those things you could call. So, well, we have spent quite some time on this where we discussed about decision hyperplanes here. In some cases, we were working with directly discriminant functions also we have discussed here, right? And of course, then we have discussed mainly this diagonal. If your covariance matrices are diagonal and same, non-diagonal and same, all these things. Non-diagonal covariances matrices we have discussed here. And in the last class, and maybe class before that, to some extent, we have discussed about minimum distance classifiers also, where you look at the discriminant function instead of decision hyperplanes that resulted in minimum distance classifiers. Correct. So in this, we have, of course, discussed a couple of things. One is based on minimum Euclidean distance based classifier. This would occur. This also, you had a question on this in your midterm exam, where you had Euclidean distance based classifier, when you will get it when you have diagonal covariance matrix with the diagonal elements being same. And then you have also discussed about Mahalanobis distance classifier. Distance based classifier. I hope I mentioned almost all the important topics that we have discussed so far as far as the Bayesian classification framework is concerned. So any questions or comments on that as far as what we discussed? Do you have any, or did I miss something important that we have covered but I did not mention here? Hopefully all the important things are covered. So then as a sixth one now, this is what we would be still covering on that in this and next few classes. That will be estimation of unknown probability density functions, unknown PDFs. This is what we will do starting from this class now to maybe next 1 or 2 classes as well. So this is again a vast area. We can go on and on with this for not less than 10 classes to do any reasonable justice, but that would be beyond the scope of this course. And I know some of you are doing statistical signal processing course. There you perhaps come across some of these estimation techniques, or if you have done detection and estimation theory course, or even in statistical signal processing course, you would come across some of these techniques in a very rigorous way. But nevertheless, we will discuss two very important estimation techniques here for the probability density functions. Those will be, we'll discuss here, maximum likelihood parameter estimation, maximum likelihood, referred to as ML. So we'll discuss ML parameter estimation method and text
MAP,
potential.
sir,
Yeah,
MAP.
correct, good. So maximum a posteriori probability. So map you call it, a posteriori probability parameter estimation. Okay, this is what we would discuss in this Bayesian classification module further. Of course, these two are for parametric. So there could be a distribution is when it can be parameterized by certain parameters like mean, variance. It could be something, the rate of decay of your function or something like that. These are useful. Then there are also non-parametric techniques, like for example, Parson windowing and all, that in the interest of time and in the interest of other topics that we would like to cover in this course, we will not be able to go into them. But these are the at least two things that we are going to discuss in this module. Okay, so let's start with the ML parameter estimation topic now. Maximum likelihood parameter estimation. Let's do that. So yeah, before we do any of these things, let's try to look back and see and question ourselves on, suppose I have given you a n number of samples, and I told you that, let's say, out of these n number of samples, these n1 samples, these particular n1 samples belong to class 1 and n2 samples belong to class 2. Okay. Now, given that, suppose if I also give you that the likelihood function, why are we talking about likelihood function, should be obvious to you by this time, because when you want to, you are doing probability of how are we finding out. So if you, from the Bayes theorem, if you recollect the way we were computing the values there, finally what you are doing, probability of x bar given omega 1 is important. What is this referred to as?
Likelihoods.
Likelihood. Into probability of omega I is referred to as prior probabilities. So from Bayes formula, this side will be probability of omega I given x bar, which is nothing but a posteriori probability. So this would be equivalent to probability of x bar. We have seen that this anyway doesn't depend on omega, so you will drop it. And if probability of omega I are equal, then finding out a class problem is equivalent to finding out the class width. If probabilities of omega I are equal for all classes, then it is equal to find out if you assign x bar to that class for which the likelihood is more. So that means it is a maximum likelihood. That's what you are doing. You are working on a maximum likelihood problem. That's nothing but a maximum likelihood problem. For varying or unequal PW, for different PWI values, okay, varying means it may sound like probability for a prior probabilities itself will vary over time. That's not the case. For different omega I values, for different values of I, then what you need to maximize? You need to maximize in that case, yeah, map estimation is same as maximum likelihood estimation in the first case. Now you need to multiply that with your prior probabilities also and then do it. So typically you could put it under the basket of maximizing a posterior probabilities problem. Do you all agree with me? So we are starting here with this maximum likelihood parameter estimation. What does that mean? I mean, that means that, say, I need to essentially compute for each class I, for a given sample x bar, what is the probability that this x bar belongs to omega I? Okay, so how do you think we can compute? What do you think, how we can compute this? Suppose I give you that this distribution, the likelihood function is Gaussianly distributed. Okay, assume that this likelihood function or PDF, you can call it rather than function. It's a probability density function. Okay. PDF is normally distributed, I gave you. So can you come up with some approach on how you could compute this? Any thoughts about that? Say, even consider a simple 1D distribution where my feature vector is just 1. I need to then know which are all the parameters that I should know to compute probability of X bar given omega I. What are the parameters that I should know to compute this likelihood value for a given X bar?
Mean and variance.
Correct. Mean and variance of the normal distribution of this likelihood function. Okay. Let's, to be general, let me write it as mu bar, and maybe the variance I would rather write covariance matrix. How do you think I can compute this? I give you now n number of samples. Okay. From that, how do you compute this? Any idea? Say what I'll do is I'll give you 1,000 samples. Okay. 1,000 samples means what is that I would give you? The X bar values. Okay. For these samples, I would give you. Now, from that, just take a simple 1D case to so that your thinking process becomes easier. Let's say I gave you X1, X2, X3, Xn values I have given you. Okay. These are all samples. That feature vector is one dimensional. Now, for these things, I am telling you that they are the samples drawn from a normal distribution. Now I need to compute the parameters of the normal distribution. How do you do that?
So for mean, we'll take the average of all the
Right.
given x1, x2 till xn.
Good. Good. And what about the variance?
And variance will take the sir, x bar square minus mu. Sir.
Expected value of X bar minus
Expected
mu
value of
whole square,
x.
right? That's what you mean,
Yes, sir.
correct? So
Yes, sir.
hope you remember the formulas that we have written. And of course, originally these are the formulas for a distribution. You have the samples of it, but still they will be pretty close approximations to what the real values are. So this we have discussed. Good. So that's how I could compute. But now, is everyone with me? So you simply, to compute the mu bar, one way I could do is my mu bar, I could even remove the bar because it is just a one-dimensional value. So what is that? You can you tell me the formula here? Mu bar equal to just
1 by
what you
n
have.
sigma xn.
1 by n summation
Xn.
I equal to varying from
1 to
0 to n minus n.
1 to n.
Or 1 to
And
n.
right, 1
X
to n,
of
what?
n.
X of
X of I.
I, correct? Right. Now, for example, how do you write the sigma square value? One by n, I think, if I am not wrong.
1 by n
Uh,
summation of
mm,
I1 to n
mm,
in bracket
mm,
xi
mm,
minus
mm,
mu whole square.
correct. Right. So that is fine. But suppose, see, this can work only if you know for sure this is a Gaussian distribution. But you can have any type of distribution. So don't expect every time a Gaussian distribution only. Suppose you might be knowing that it is an exponentially decaying distribution. Okay. And or this is a logarithmic distribution or whatever it is. There are quite a lot of possible ways are there even within parametric distributions. So then how would you achieve that? This is fine as far as you have just a Gaussian distribution. But what this maximum a posteriori probability estimation technique will let you do is, irrespective of the parametric distribution being Gaussian or something else, if it is something else, then to characterize that, maybe mean and variance are not good enough. You may have some other parameters. Assume that there is some exponentially decaying distribution. The rate at which it is exponentially decaying, assume that e power minus times lambda times x square is there, something like that. Okay, then lambda is what you want to know. So these two techniques, maximum likelihood ML parameter estimation and map parameter estimation, will let you compute these parameters for any general distributions that can be parameterized. That means you can, but again, there is a catch here. You should either know, means you should know what with what you could kind of approximate the distribution with. That at least you should know. Otherwise, you cannot parameterize it. But then its parameters, you can find it using these distributions. Clear so far? So now, essentially, you could say now probability of x bar given omega I. Okay, this is what you have to find out. Now, each class is characterized, each omega I class is characterized by a set of parameters. Let me call those parameters as theta I bar. Okay, for example, has this been a Gaussian distribution, that would be mu I. Again, the theta I bar can have, I don't know whether I should put bar there, because each of the components there within that also can be vectors, but assume I hope you understand that. So it's okay, I may do a little abuse of notation, that should be okay. So each is characterized by theta I, and my goal now is to compute these theta I bar. Okay, so first assumption here, there are some assumptions that we are going to make in order to make this problem solvable. Is see, for a given class, I have a samples, then I assume that the parameters of a given class are independent of the parameters of the other class. In other words, the mean and variance you consider here that I need to estimate for this class are independent of the mean and variance values that I would be getting for other classes. Let's say I'm doing it for omega 1. I don't have to worry about omega 2 at the time of calculation of omega 1. Okay, in practice, this might not be true for some distributions, like like two Gaussian distributions which are overlapping. Then maybe there are instances where this could get violated, and you may have to then resort to something like expectation maximization, where you iterate between them. But for now, we will not go into that level of complexity. Just what we would do is, likelihood functions are whichever are they are for theta I, if you consider, then they are dependent only on the samples of this class and parameters of this class estimated from those samples, and do not depend on the parameters of other class. So so dependence of, so I would write, then how should I write is, so what I will do from now onwards is, basically I want to compute probability of x bar given omega I. This value is dependent on the set of parameters theta I with the above mentioned assumption. Then now I would rewrite this as probability of x bar you are given a theta I. Okay, hope I am clear. You don't have to worry about the samples of other class and the parameters estimated from those samples. That's my first assumption I am going to do here. Second assumption, what I will do is, let's say x1 bar, from this I am drawing different samples, x3 bar and so on. And let's say this class has n number of samples. So I would write this as xn bar. So these are the random samples drawn from, these are the random samples drawn from probability of x bar comma theta. Okay, this distribution, whichever is there, those are the random samples that are drawn. Now, so it is from all these, see, each sample is having a, all the, suppose if it is having feature vector of dimensions L, each one is a vector of L, such n vectors are there. Okay, from this you are going to estimate the parameters. So I would write now this as a single matrix here, from which I'll do. So let me put a bold letter there. I won't keep bar there anymore because that's a matrix. Let this x bar be x1 bar, x2 bar, and so on, xn bar. Okay, so that means now my problem, I would write it as, since I have these things, probability of x given theta. So, well, this is what I could write the likelihood function, where I am putting all n samples in one go. This is, see, actual distribution I don't have, but all I have here are the samples drawn from that distribution. So I'm writing it as probability of x comma theta. Okay, and it is from here I would like to make some estimation of the parameters. Just trying to add one more point here. In the assumption one I made, you could also think about it in terms of what I have, what you could see here in the Bayes theorem. We assume that the probability of omega I are equal. So that means while you are drawing samples, this is another important thing. Then only you will that classify as if you are doing maximum likelihood based on that. If you are assigning to the classes, it inherently or implicitly assumes that probability of prior probabilities are same. Okay, so perhaps the one which mentioned there, you could interpret that in terms of this. That also you could consider as one of the assumptions here. Okay, now what you will do is probability of x given theta, I could write it as probability of x1 bar, x2 bar, and so on, xn bar, and for a given theta value. So assuming that all the samples are statistically independent, then what can you, so this is how this has been defined. Now with that, what can you say about x1 bar comma x2 bar and so on, xn bar for a given theta value? How could you write that if I make that assumption? I'll write portion of the expression, then you tell me the remaining. It is multiplication of k equal to 1 to n, probability of, you now tell me.
xk.
Right, good. xk bar for a
Given
given
theta.
theta. Okay, very good. See now, your theta, pay your full attention here, otherwise it looks like a sudden jump if this point is not clear. Assume that you have a distribution that is parameterized by theta, and these are the samples drawn from that are these n samples. So if your theta is correct, if you have picked the right value of theta, case 1, case 2, your value is, theta value is not accurate compared to the one that we mentioned, that we picked up beforehand, before this case. In which case do you expect this function, this probability function, to be maximum?
Case one will be more
Correct.
value.
Right. See, when you already have samples with you, which are drawn from an estimation, it is like, I assume that I have a circle. I have drawn some points. These are samples, are just a few points on the circle. This circle, assume that is centered at 0, 0, that for sure there is a radius r. Now, I'm taking different values of r, and then if I'm computing that probability that this xi be the sample there that belongs to r, okay, I will see then Euclidean distance to the circle to this and do that. When will this probability component value will be more? When I pick the right value of r. Of course, you could think about that in a same thing about a line. I have fitted a line here in all your, I think you have done somewhere least square fit of line and everything. When that fit be the maximum, if I have different lines possible, if I compute what is the probability that these points belong to this, how can I compute that probability? I just simply compute the Euclidean distance of these points to a given line parameterized by, let's say, for simple case, let's consider by M and C, and I'll probably sum them up. If it is probabilities, I can multiply them there, just like what we have seen there. And this will be maximum when you have picked up the right parameter. And now the approach is very simple. You vary the theta values within a possible range, and for each of those theta values, you compute this expression given here, and finally pick that theta value which results in maximum probability, maximum of this function. This should be absolutely clear to you, because that forms the basis for the rest of the discussion and also for maximum likelihood estimation. So I would like to ensure that this is clear to you.
Sir,
Yeah,
sir,
please.
here theta is characterizing in the sense like theta is having value of mu as well as the mean and variance both, sir.
Correct. So if it is a Gaussian distribution, your values are mean and variance. If this is something else, for example, if it is some other distribution which is exponentially decaying, your theta might be the decay function you might have. If it is some other function which has a kind of a different value, so which is calculated by, let's say, some A, B, C parameters, that will be your theta.
Okay, sir, right.
Now, is the intuition clear based on that?
Yes, sir.
Good. So I'm going to put the same thing in the mathematical form here. Let my value that I would be getting here, I'll call it as maximum likelihood estimate with theta ML cap. This is nothing but argument that maximizes. The thing that I would vary is theta, and the function I would look at is k equal to 1 to n probability of xk bar comma theta. This is the maximum likelihood estimate. All I have written is, now I vary theta, compute this function, and theta ML cap is that value of theta for which this function is maximum. So you could think of it, let's let your let's say your theta is a single unknown parameter, so that I could draw you and show you. Let theta be a single unknown parameter. What is it that you are essentially doing here is you are going to vary your theta value here, and this whole function I'm calling it as probability of x given theta, is it not? That's how I am calling this, probability of capital X given theta. So I choose different values of theta here, and I would calculate what all I am getting the values here, and it is maximum, let's say at this point, and this will be my theta maximum likelihood estimation I would take here. Of course, then you could draw up to two-dimensional thing. Beyond that, you will not be able to plot. But this is the basic idea on how you compute the maximum likelihood of a distribution. But here, keep in mind that the very implicit assumption here is you already know the type of distribution. You do not know its parameters, values, but you know how it is parameterized, whether it's a Gaussian, Dirichlet, exponentially decaying, whatever it is, Poisson, whatever it is, you know what is the type of distribution. Then you are playing with by varying or giving different parameters there. And then you are computing this probability of X given theta, and finally choosing those values of theta for which this probability function, this likelihood function is maximum. So then I'll take one more step here. Well, this function has been given to me. How do I know where it has maximum? Suppose I assume that this function is an analytical function I gave you. So can you right away, I would like to know where this function is maximum. How can I find it out?
So by differentiating
Differentiating with respect to?
theta.
Right, differentiating, that has to be very clear. And of course, this theta could be, keep in mind that it can have multiple parameters also. Okay, for simplicity, I write it as theta here and look as if you are dealing with just one parameter, but always keep in mind that this could result in taking derivatives with respect to multiple parameters. And of course, in practice, what you may also do is you assume you fix one value and just play with the other value and find it. But essentially, what you need to do here is dou by dou theta of that expression I am writing here, k equal to 1 to n probability of xk bar given theta. This is what? Then what you should, taking this derivative and equating it to?
0.
0. Very good. Equating it to 0. Then hope you recollect the trick that we did with the discriminant functions, where sometimes calculating these probabilities can have exponential functions and all these things. So that will make your calculations complicated. So you may rather prefer applying a monotonically increasing function on top of it. And then since it's a monotonically increasing function, still you could make its derivative equal to 0. So keeping in view of the Gaussian distributions that you could expect, what is the monotonically increasing function that you would consider?
Log.
That's right. So I would write here L of theta bar is equal to natural logarithm of, now the same thing, k equal to 1 to n probability of xk bar comma theta. This is the function that I would take now. So since this is a monotonically increasing function, what would be the effect of that? That means to find out the theta bar, I could still apply a derivative there and equate it to 0 to get the theta value. So I could again do dl of theta bar. Okay, I'm calling it as L of theta bar. So that function, you take the derivative with respect to theta. So what would be that value now? So multiplications, what would happen to multiplications when you take a logarithm there? Multiplications would become
Summation, sir.
Summations, correct. You have seen it enough number of examples by this time. So this would become k equal to 1 to n and dou by dou theta of probability of xk bar comma theta. I made some mistake here. Can you correct that?
Logarithm.
Logarithm, right? Good. That's what I have forgotten while I was writing. Probability of xk bar comma theta. Okay. This I have to make it to 0 to find the maximum. Now what? That implies I could also write dl of theta by dou theta is equal to summation k varying from 1 to n. What could be that value? Dou by dou theta of natural logarithm of p of theta. So tell me, how should I write that now? 1 over probability of xk bar colon theta into dou by dou theta of probability of xk bar comma theta. This is what I mean to see. Natural logarithm of probability of xk comma theta, and with respect to theta I'm doing. So natural logarithm of x is 1 by that function. Then for the inside I need to just take one more derivative there. So dou by dou theta of this thing I am writing. Okay. Are you able to follow with me till here?
Yes, sir.
Let me give you an example to work out. So you please, by next class, you please work it out. So assume that your probability of xk comma sigma square is equal to 1 over square root of 2 pi into sigma into exponential of minus of xk minus mu whole square by 2 sigma square. So assumption here is that I know the mu value already somehow. Okay. Now you compute sigma square. If you do maximum likelihood estimate on this, see, all you need to do is compute this L of theta. Okay. Take the derivative of that, make it equate to 0, then see what you are going to get here. Is it same as what you have got earlier, whichever expression we thought? Irrespective of this maximum likelihood estimate, we have thought of something else. Okay. We have written the expression in the very beginning here. This is the expression. So will you be getting the same expression or something else? You please work this out for the next class. This is one thing you have to, first problem you have to work out. Second problem is, now assume that you know the mean value, you know the variance, but you do not know the mean value. So when I say that, you just consider in the first problem as if the mu is constant. Okay, you don't have to worry about its derivative. Now in the second problem, you consider sigma as constant, so you don't worry about that. Now the same Gaussian distribution I would take here. Sorry, there was some cut there. Xk minus mu whole square by 2 sigma square here. Now in the second problem, you assume that you know sigma. What you need to, the parameter you need to compute using maximum likelihood is mu. So you compute mu ml. Okay, these are the two problems that I'm giving you for the before the next class. Very simple, but you need to spend some time. Unless these things are clear to you, you'll find the rest of the things not so comfortable. So please do these things before the next class. Okay.